Welcome to the lecture that involves gases, the chemistry of gases. We're going to start off talking about the kinetic molecular theory and some of the simple gas laws that we discussed in regular high school chemistry, Boyle's law and Charles' law. Alright, so before we get into gases, let's talk about straws. Because what kid doesn't like to drink from a straw and blow bubbles with a straw and see how long of a straw and twisty of a straw you can get to make your drink so fun. Anyway, so our question for this unit is, how do straws work? Well, a lot of people actually don't quite, understand exactly how straws work. So let's go through this a little bit. Has to do with pressure. Sucking creates a pressure difference between the inside of the straw and the outside of the straw. When we suck, we remove some of the air molecules from inside of the straw, which lowers the pressure on the inside of the straw. Okay? Now, once that pressure is lowered on the inside of the straw, now the pressure on the outside is greater than the inside. And so the external pressure is pushing the liquid up the straw. So it's not that your mouth really technically sucks in the liquid. It's that the air around the straw and pushing on the drink actually pushes up the liquid up through the straw and into your mouth, because your mouth has decreased the pressure inside of the straw. Dun, dun, dun. So there you go. That's how straws actually work. And so straws have to do with gas and pressure, and that's where we begin. With gases and what's called the kinetic molecular theory, a model for gases. A simple model for understanding the behavior of gases is called the kinetic molecular theory. It's going to basically predict the correct behavior for gases under many different kinds of conditions. Now, there are 4 assumptions that the kinetic molecular theory kind of goes by, and these assumptions include a gas being a collection of particles in constant motion. Okay, so whatever gas that gas particles you are going to be investigating, they have to be in constant motion, and that's basically kind of the definition of a gas, is a collection of particles that are in constant motion. Now, these particles are not attracted or repulsed by each other. They are simply moving and colliding with each other and with the walls of the container that they're in. So there's no attraction, no chemical bonding, nothing like that going on, no repulsion, no electrostatic forces of any kind, just simply moving and colliding. Now, the third assumption is that a lot of space is between the particles of the gas compared to the particles themselves. So the particles are very tiny and they are distanced by large spaces. And the fourth is that the speed of the particles increases with increasing temperature. All right, which basically, if you remember the definition of temperature, it is how fast molecules move in a substance. So it makes sense that the speed of the gas particles is going to increase if you increase the temperature, because you're moving the gas molecules faster. All right, so let's dig deep. This kinetic molecular theory is constant or consistent with the properties of gases that we know and we can observe. So gases we know are compressible. The atoms and molecules that make up a gas have a lot of space in between them. All right, that's what one of our assumptions for the kinetic molecular theory stated. And if there's lots of space in between them, then hey, that space can be removed easily and we can squish those atoms and molecules closer together. So if we take a look at this picture, okay, this is gas being compressed. Here's the initial volume, okay, and here is, after we add some pressure to it, here's the second volume. And we can see that in the initial volume there's a lot more space between the molecules, and in the final volume there's less space in between the molecules. Now, liquids and solids are not compressible. Okay, we see down here, this is solid, liquid, and gas. These represent the states of matter. And we can see that in a solid and a liquid, those molecules or atoms are already really close to each other, so we can't really compress those molecules any closer to each other. So gases are the only state of matter that are compressible. Now, the second property of gases is that they assume the shape and volume of their container. Okay, so like we see in this picture right here, okay, the gas, basically it says, if you have a gas in a container, it's going to take up the whole space. And it's, if it's a unicorn-shaped container, then the gas will take up a unicorn shape. All right, and that's because gas molecules, remember, are in constant random motion, and they don't interact with each other. They are just moving and colliding, so they're going to be moving in the entire space or capacity of that container, and so they will take up the shape and volume of whatever container they're in. All right, and then last but not least, gases have low densities, okay, and that's because again, they have a lot of empty space in between them, in between the atoms and molecules. So, for a particular volume, if there's a lot of empty space, there's not going to be as much mass. And so little mass per volume is going to equal little density. All right, so in gases, when we're talking about pressure, so we have to kind of go over and define what is pressure. Pressure is the result of the constant collisions between those atoms and molecules in the gas, both with each other and with the walls of the container or the surfaces that are surround them. So pressure basically is force divided by area. It's how much force we're putting on in a certain, in a certain area. So what I like to kind of think about is if, the difference between like flat shoes and high heel like stiletto shoes, right? So if you are wearing flat shoes and you're on a particular surface or whatnot, that you're gonna be exerting a certain amount of pressure. Okay, you have this force of your body weighing down on the ground area around you, and that you're going to put a certain amount of pressure on the ground. However, if you were wearing stiletto heels instead of just flat shoes, you'd be putting a lot more pressure. Okay, and that's because the area that the shoe, that all of that force from your foot and your body is making is now on just a little tiny little heel, okay, versus the entire flat of your foot. And so if you have really small area and the same amount of force, you're going to be basically putting a lot more pressure on the ground. So that's kind of how pressure works. Now, pressure is going to depend on a lot of factors, and one of those factors is the number of gas particles. So, and that kind of, that's kind of common sense, right? If you have fewer gas particles in a container, okay, like we see here, they're obviously not going to be colliding with each other very often, or colliding with the container walls very often, and so it's going to equal low pressure. Okay, versus if there's a ton of gas molecules colliding with each other and the walls of the container, you're going to get a lot more collisions, and so there's going to be a lot more pressure. So that is one thing that we do have to keep in mind when we're talking about pressure, is the number of gas molecules. So as we're talking about pressure, let's take a look at all the different pressure units. You may or may not have recalled from regular chemistry, there was a bunch of pressure units, okay, a bunch of different ways we can measure pressure. So let's take a look at those different ways. So the simplest way to measure pressure is what we call by an atmosphere. An atmosphere is basically the pressure of the atmosphere, the air around us, when we are at sea level. So 1 atmosphere is the pressure of the air at sea level. Now, just kind of give you some comparison. A bike tire pressure is 6 atmospheres. Okay, and versus Mount Everest, the tallest peak in the world, is only 0.31 atmospheres. Okay, so it's kind of a little comparison for you. Now, another pressure unit is called the pascals, PA. This is actually the SI unit of pressure, so it's the one most commonly used in scientific studies and around the world. Different scientists and different different countries are going to be using the Pascal to keep their measurements in line with each other. Now, a Pascal is equal to 1 Newton per square meter, and a Newton is basically a way we measure force. So it's force divided by area. So like we had saw before, pressure is force divided by area, or newtons per square meters. All right, now, so 1 Pascal is equal to 1 Newton per square meter. Now, when we relate that to atmospheres, okay, 1 atmosphere is actually equal to 101,325 pascals, okay, which is a huge number. So typically, when we're working with pascals, we're actually going to be working with kilopascals. So remember, kilo means 1,000. So we're going to divide pascals by 1,000 and just move that decimal over 3 times to the left. Okay, and so what we're going to get is 101.3 kilopascals. So that's what we usually are going to be measuring in when we're talking about pressure, is that kilopascals. And in fact, if we look at this pressure gauge right over here to the right, we can see here it says kPa. All right, so this pressure gauge measures in kilopascals. All right, another pressure unit, one we use here in America, is pounds per square inch, or PSI. Okay, so that means pounds per square inch. So how many pounds of force are you putting on a square inch at a time? And again, to relate that back to atmospheres, 1 atmosphere is equal to 14.7 psi. We can see here in this gauge, if we were to use this gauge to measure pressure, it would tell us in units of psi. All right, still more. Yes, more ways to measure pressure. All right, so you may or may not have seen Mr. Fryer used to have one in his room, but alas, it broke. This is called a barometer. It's one of the ways we can measure air pressure. It's kind of like the old school way to measure air pressure before digital technology. And what this is that basically it is a dish or container that has mercury in it and a glass tube that has been evacuated of all air. So basically it's a vacuum. Now, atmospheric pressure, okay, is going to put pressure on the container that has the mercury in it, and when pressure pushes down on the mercury, it's going to start rising on the inside of the glass tube. Okay, and so however much it rises is going to be equivalent to a certain amount of pressure. All right, so because this barometer is using mercury and it's measuring the length of mercury in a glass tube, one of the pressure units is millimeters of mercury, or mmHg. Millimeters is mmHg is mercury's symbol on the periodic table. All right, so millimeters of mercury again originates from how pressure is measured with a barometer. Now, interesting to note, why do we use mercury? Well, if we tried the same little trick with with water at sea level where there's 1 atmosphere, okay, that atmosphere would actually push up water into a vacuum tube to the height of 10.3 meters, okay, which is not very realistic. I mean, that's going to be like way bigger than a typical room is going to fit. All right, so we need something a little bit more dense, but also still in the liquid form. So so that it can rise and fall and take the shape of the container or the tube that is there. So what is his name? Torricelli, who we're going to talk about in just a sec, figured, hey, let's use mercury. It's a metal that's much more dense than water, and it's also conveniently a liquid. So he used mercury in the first barometers, and luckily mercury is much more dense, like I said, so it only pushes up to 760 millimeters at a pressure of 1 atmosphere. So if we know that, we can use this little conversion here. 1 atmosphere equals 760 mmHg, or millimeters of mercury. All right, the last type of pressure unit that we're going to talk about, at least, is the torr. And basically, it's the same as millimeters of mercury because it's just named after the guy who invented the barometer, whose name was the Italian guy Torricelli. Okay, so 1 millimeter mercury equals 1 torr. So that's why if you take a look on the periodic table, on the back side there is on the bottom a bunch of pressure units, and they're all equivalent to each other. And it'll say 1 atmosphere is equal to 760 mmHg, okay, which is equal to 760 torr, because mmHg and torr are the same, going to be the same type of units and numbers. Oh yes, and I did forget to mention that Torricelli is this fine-looking fellow right here. All right, so if we have relationships between numbers, then we have conversions and conversion factors. So let's take a look at how pressure conversions are going to work. Basically, it works the same way with like our bridges that we were doing earlier in this semester, where we're going to have to cancel our units. It's all about canceling units when it comes to chemistry and pressure conversions and any type of conversions, actually. All right, so let's take a look. The first is to not convert, but to convert 0.311 atmospheres to millimeters of mercury. All right, so again, we always start with what we're given, 0.311 atmospheres. And we want to get to millimeters of mercury, so we're going to put our millimeters of mercury on top. And in order to cancel out our atmosphere units, they go here on the bottom. All right, so our atmosphere units are going to cancel. We can put in numbers. We know that because of the relationships we were just talking about, that 1 atmosphere equals 760 mmHg. So the 1 goes with the atmosphere on the bottom, and the 760 goes on the top with mmHg. Now when we multiply the top numbers and divide by the bottom, we're going to get 0.311 times 760, and then divide that by 1. And in the end, you get 236 millimeters of mercury. All right, so let's try one more together as we do this. It says a high-performance road bicycle tire is inflated to a total pressure of 125 psi. What is this in millimeters of mercury? Well, let's figure that out. We always start with what we're given, 125 psi. All right, now to get rid of psi, we need to put him down here on the bottom. And we're asked to go to millimeters of mercury. Now, like I was saying before, we actually don't have a direct conversion between psi and millimeters of mercury. The one that we do have that's common to every one of them is atmospheres. So let's first convert to atmospheres. Okay, and then once we convert to atmospheres, we can cancel out atmospheres and get our millimeters of mercury. All right, so we've got our units set up. We got it set up so psi is going to cancel, and we got it set up so atmospheres are going to cancel. And all we're left with is mmHg. So this is going to be perfectly set up, so let's put in our numbers. Now, 1 atmosphere is equal to 14.7 psi, like I just mentioned a few minutes ago. And in our second conversion factor, 1 atmosphere is equal to 760 mmHg. Now, when we do this, we are going to get 6462.6. All right, so we got to keep in mind our sig figs. Okay, we start out with how many to start? Well, 1, 2, 3. So that means our answer should have 3. So we got to round this to 6460 mmHg. Bam. There you go. A little unit conversion fun for you. All right, so let's keep on going. All right, so now we know a little bit about pressure and that it has to do with gases. Let's take a look at our first gas law that we're going to investigate. It's called Boyle's law. Now, like I said a little earlier, relationships between gas properties are described by gas laws. They basically are going to show how if you change one property of the gas, it affects the other properties of the gas. So in this case, for Boyle's law, the pressure of a gas sample depends on its volume. If the pressure and amount of gas, if the temperature and the amount of gas are kept constant, what happens is that pressure increases when volume decreases and decreases when volume increases. If you can imagine a soda can and you crush it with increased, what happens when you push down with increased pressure? Well, the volume decreases. It starts to crush. All right. Same thing, if you were to take off that, pressure, like on a spongy thing or something, so you have a bunch of pressure and you take it off, the spongy thing goes whoop, okay, back to its original volume, so the volume increases. All right, so basically what this means is that volume is proportional to 1 over P, okay, or the inverse of pressure. So this little alpha fishy thing, okay, is a symbol that means proportional to. Okay, so volume is proportional to 1 over P. So it means that pressure and volume are inversely related. So increasing one of them is going to decrease the other. So if we increase pressure, we decrease volume. Or if we increase volume, we decrease pressure. Okay, so let's take a look a little deeper at this gas law. If volume is decreased, that means the gas is crowded into a smaller space, right? So if we take a look at this picture down here, here's our original volume. Okay, and if we put pressure on it, if we increase pressure, we're going to decrease the volume, the space in there. Okay. Now, if we take a look at the inside of the container, okay, at this decreased volume, the gas is basically crowded into a smaller space. So what that means is that you're going to get more collisions. And the more collisions means the increase in pressure. So on the inside of the container, the pressure of the inside of the container is going to increase when you decrease the volume. Now, this has practical purposes. If you've ever seen scuba divers or even been scuba diving yourself, you know that pressure is huge. Pressure can be, basically you have to regulate pressure in order for it to to not kill you. So if we think about, you're scuba diving down, to a depth that exerts, 3 atmospheres of pressure, and say you hold your breath. Okay, so diver inhales a lungful of 3 atmosphere pressure and then swims quickly to the surface while holding his breath. I should say breath, not breathe. Well, what happens? Not good things happen. Okay, so if we think about this, as we go up to the surface, okay, we're going to decrease the pressure. Okay, so if we're starting down at a pressure of 3 atmospheres and we go up and we decrease that pressure by a factor of 3, that means we have just increased our volume by 3. Okay, so the volume of our lungs by 3. So if you inhale and hold your breath and then quickly swim up, you're going to basically put a lot of strain and pressure on your lungs. They're going to expand basically threefold. Ouch, basically, is what the point is. So that's actually, I guess, the number one rule of scuba diving. I don't know, I've never been. But is to never hold your breath. You always want to breathe in and out as you go slowly up towards the surface, so that your body has, continually regulates itself and the pressure around you. All right, so let's take a look at doing some calculations with Boyle's law. So the important equation here is P1 times V1 equals P2 times V2. Okay, and so because pressure, when pressure increases, volume decreases. On a system, if we take a look at a particular situation of a gas inside of a container, we can take a look at before and after. If everything else is held constant, temperature and the temperature and the number of molecules, then we can put those the initial readings of pressure and volume equal to the final readings of pressure and volume, because they're both going to be equal to the same constant. All right, so let's take a look. It says calculate the pressure of a gas that was initially 765 mmHg and 1.78 liters, and later compressed to 1.25 liters. All right, so let's put basically down what we have. So our initial pressure, because remember mmHg is pressure. Initial pressure is 765 mmHg. And that means our initial volume was 1.78 liters. Now it's all about the key words like later, final, initial, those kind of things. Start out with. All of those are going to kind of give us a clue about what numbers are for initial and what numbers are for final pressures and volumes. So later means obviously later, like final. So we've got volume, V2 is 1.25. So that means we have to figure out what the new pressure is. So if we use our P1 times V1 equals P2 times V2, we'll have 765 times 1.78 equals X times 1.25. So if we do our little very simple algebra here, divide both sides by 1.25, our final pressure is 1090. Okay, and that's going to be mmHg. And that is definitely taking into account sig figs. Okay, we started with all of them being 3 sig figs, so we need to have our answers 3 sig figs. So 1090 is 3 sig figs. All right, and so let's kind of just double check ourselves to see if this answer makes sense. In fact, it's super easy to do, so always kind of get in the habit of doing it. Now, we see that in this problem, pressure decreases. So if pressure decreases, that means, I'm sorry, not pressure. We see that volume, this is L, liters is volume, so volume decreases, so that means pressure should increase. So that is exactly what we saw. Our initial pressure was 765, and our final pressure is 1090, which is definitely greater than what we started with. All right, so here's a you try it. A cylinder equipped with a movable piston has an applied pressure of 4 atmospheres and a volume of 6 liters. What is the volume of the cylinder if the applied pressure is decreased to 1 atmosphere? Okay, so again, you are going to use P1 times V1 equals P2 times V2. I'll help you get a little head start on this, and then you can finish up the rest of the calculation. So it says that it's equipped with a piston that has a pressure. So here's our P1 of 4 atmospheres, and its volume is 6.0 liters. What is the volume of the cylinder if the pressure is decreased? So here's our P2 to 1 atmosphere, And so you have to figure out what that volume is. Good luck. All right, so that was a little investigation into Boyle's law, the relationship between pressure and volume of gases. Now let's take a look at Charles' law. Charles' law is going to investigate not volume and pressure, but volume and temperature. All right, so we see basically Charles' law all the time in hot air rising. Why does hot air rise? Well, the volume of gas sample, if it's at constant pressure, is going to increase with increasing temperature. So as temperature goes up, then the volume is going to go up. Okay, if volume goes up, and if we take a look here at our density equation, if volume goes up, if we increase volume, that means we're going to be dividing by a bigger number, which means our density is going to go down. Okay, so it decreases density if we increase volume. So the lighter something is, if it becomes lighter than the regular atmospheric air, then it's going to start to rise. Now, what this means when we see that as you increase temperature, you increase volume on a graph, that volume and temperature are linearly or directly related. Again, if the temperature increases, the volume of the gas is going to increase. And we can see that on these graphs here. As temperature increases, volume increases. We get a nice straight line. Now, if we extrapolate our data, if we look at this second one here, and we extrapolate our data, our line all the way down to hit, so that hits the y-axis, or y-axis at 0, so 0 volume. Gases should have 0 volume at negative 273, and that should say not 2,730, but it's negative 273 degrees Celsius. Okay, and so that is the temperature at which gases are going to have 0 volume. Okay, and that's what we call absolute zero, or 0 Kelvin. All right, like I've stated before, the volume of a gas and its temperature, now we have to be specific. We have to be specific in saying that its temperature is in Kelvin. Always, 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 when working with gases, make sure that you convert Celsius to Kelvin. And if you don't remember, you have to add 273, okay, to the Celsius to get Kelvin. So volume of a gas and its Kelvin temperature are directly proportional, or directly related. So increasing one by a factor increases the other by the same factor. So if you increase the temperature by 2, you're going to increase the volume by 2. All right, so if temperature increases, that means that, remember, temperature is how fast molecules are moving. So if you increase temperature, you're going to make the molecules or particles of gas move faster, which if they move faster, they're going to be colliding more with each other and taking up more space. So the volume is going to increase. Okay, and when we count for Charles' law, we're going to assume that the pressure is always kept constant. All right, so let's take a look at calculating with Charles' law. So in the previous slide, Charles' law was V1 over T1 equals V2 over T2. Okay, because if you increase volume, you're going to increase temperature. If you increase temperature, you will increase volume. All right. In this question, it says a 2.37 liter sample of gas at 298 Kelvin is heated to, okay, so that means that what we just read was before, and now it's being heated to, so that's after. Okay, so that's going to be our 2's. So it's heated to 354 Kelvin with no change in pressure. Determine the final volume. So we're going to be solving for V2 because it asks you for the final volume. All right, let's see what the rest of these are. So V1 is 2.37 liters because that's the volume that was mentioned first. And its temperature to start with is 298 Kelvin. Now it says it's heated to a different temperature, so that must be our T2. And it's asking to solve for V2, which is our X. So if we plug in these numbers to the equation, we'll have 237 over 298 equals X over 354. Alright, what we'll do is we'll cross multiply. We'll do 2.37 times 354 equals 298x. And with some very simple algebra, we can get x by itself. And x is going to equal 2.82 liters. Alright, so again, let's see if this makes sense. So what we're doing is we are increasing the temperature. Okay, we can see that right here. We're going from 298 to 354. So if we increase temperature, then we're going to increase the volume. And that's exactly what happened. We started with 2.37, and now we end up with 2.82, which is definitely higher. We've come to our last slide here. Another you try it calculation. It says a sample of gas has a volume of 2.80 liters at an unknown temperature. Dun, dun, dun. When the sample is submerged into ice water at 0 degrees Celsius, there should be a little degree sign, its volume decreases to 2.57 liters. What was the initial temperature? And again, always assuming pressure is constant. So, first thing we need to do is figure out what these numbers are. So a sample of gas has a volume of 2.80 liters. So that must be our initial. And an unknown temperature. So our T1 is going to be our X because we don't know it. When the sample is immersed into ice water, so that's it's going to represent our T2, that's ice water at 0 degrees Celsius. Now remember, we always have to have which unit? That's right, Kelvin. So in order to change 0 degrees Celsius into Kelvin, we have to add 273. So T2 is going to be 273 Kelvin. All right, and it says its volume decreases to 2.57. All right, so what is the initial temperature? All right, so there you've got things laid out. You do the math, and if you have any questions, make sure you ask next class. We'll see you then.